welcome to this class, and we have been discussing scrambling, and which is basically part of the 5G transmit chain, and we will finish discussing the transmit chain today, and then we'll recapture it once more from beginning till end, so that the entire transmit chain is amply clear to us, and then we'll move on to the physical layer receive chain. Okay, so this is the agenda. Okay, so we'll discuss scrambling and modulation first. And to recapture what we have studied till now is basically this part of the chain, wherein you get a transfer block, append transfer block CRC. Then if the transfer block is greater than a certain size, you will have to segment it. The reason for segmentation is basically that LDPC encoder is designed to encode only a certain maximum size, okay, and that certain maximum size is 8448, okay, which is denoted by number KCB. And once you segment it, then there is this code block CRC, which makes sure that once the hybrid ARQ triggers, you don't have to ask for the retransmission of the complete code block, a complete transport block. Okay, you can ask for the retransmission of only a single code block. Okay, if this CRC is not there, then the receiver will have to ask for the retransmission of complete transport block. Okay, so it avoids that, and then after that LDPC encoding is done. Okay, so then the key idea behind LDPC encoding is that it has a mother code rate of 1/3. Okay, and any other rate which is demanded by the user, okay, or basically by the receiver, is generated from this rate 1/3 by this rate matching module. And then the output of this LDPC encoding is basically rate 1/3, which is denoted by N, and the output of rate matching module is denoted by E. Okay, right? And then once these, so the rate matching module basically takes in one LDPC encoded block and then rate matches it, then gives it to the interleaver. Okay, what interleaver does is basically it is a row column interleaver, and it divides the input stream into the Q number of parallel streams. Okay, and then reads them column wise. Okay, right? So that, and the reason for this interleaver is basically because it helps in avoiding the burst errors, and LDPC decoder is bad in correcting burst errors, so it avoids that. Okay, then there is this code block concatenation. That is a very simple module. It takes in all these code blocks and then concatenates them. The notion of code block is lost after this. And then there is the scrambler. That's what is our focus now. And the scrambler, it takes in these bits and scrambles it with the code sequence. Okay, and that's what we are learning now. And we'll recapture it, and then I'll tell you what is the reason. Okay, why is it required? And it is required for certain modulation schemes, which is beyond 4 QAM. It is required for higher order 16 and above. Okay. And then there is a modulation. Okay, so modulation, we'll see what these modulations are. 5G allows from 4 QAM to 256 QAM. Okay, once we see this, then we'll again run through this, look at the different numbers, and then that will like reinforce whatever we have learned till now. Okay, we have learned this chain in bits and pieces. Now we'll do it together, and that will consolidate our learning. Then after that, in the last part of the class, okay, I'm going to basically look at this receiver chain and how different modules work. Okay, let's start with this scrambler module. And what is the output of this output length of the code block concatenation? How many bits? G bits. Okay, because each of them is E, and then when you concatenate them, you get G bits, which is G. What is G? G is E by C. C is the number of code blocks. Okay, and you are allowed to transmit only G bits. Okay, that's the number we have calculated. Okay, so there is a block of G rate matched and concatenated bits. We are denoting them by like this. Okay, now what is this scramble bits we saw in the last class? Okay, so this is the input bit sequence, and this is a some code which is given to you. Okay, we'll generate this also later in other classes. Okay, I'll tell you how this is generated. This is called a scrambling sequence. Okay, and what are we essentially doing? What is this scrambler doing? It is taking this input bit sequence and then XORing it with this scrambling sequence. Okay, so the length of the scrambling sequence, of course, has to be equal to G, capital G. Okay, right? And we denote this scrambled sequence as B tilde I. Okay, the C of I is a pseudo random sequence. What is a pseudo random sequence? We discussed it. Okay, it's random. Okay, and then but you know it exactly. Okay, so what is, if you take in some B of I, it's only the XORing operation which is happening over here. So you take in this bit stream B of I and then XOR it with some sequence C of I, which you have to generate. Okay, and standard like tells you exactly how to generate. Okay, and we learn that also. So if you do the scrambling operation is XORing, and we know that if 2 bits are same, XORing gives you 0. If 2 bits are different, XORing operation gives you 1. Okay, right? So that's what it is. Okay, you can do this bitwise XORing and you'll get this sequence. Right? So this is what we saw yesterday, and this is how it is done. Right? Okay, but why it is done, that's something very subtle, and that's what I'm going to teach you. Okay, but for that we'll have to see what kind of modulation schemes 5G allows, and it is needed for certain modulation schemes. Okay, if 5G allows only this QPSK, you don't need this scrambler. That's what I want to show you. Okay, it is because there are other modulation schemes, you need them. You need this scrambling module. Okay, so and that's where I like this will make a comeback. Scrambling will make a comeback. The reason behind the scrambling. Okay, let's see this modulation block first, formally being introduced for the first time, and this is basically from this section of the standard. Go back and check. Okay, how modulation is actually specified. I'll show you that. Okay, so this basically starts from 4 QAM to 256 QAM. I should tell you this, that this is only for PDSCH, okay, which is basically the data channel. Okay, right? And if it is like control channel, BPSK is also allowed. We'll see that. Okay, but it starts from QPSK, which is 4 QAM, goes up to 256 QAM. And as far as I believe, 1024 QAM has also been introduced. Okay, and if you listen to people, they're talking about introducing 16K QAM also, or 4K QAM, 16K QAM. Okay, basically what is happening, if you have a 4 QAM over a single resource element, how many bits you can transmit? You can transmit 2 bits. Okay, if it is 256 QAM, you can transmit 8 bits. Right? If it is 1024, you can transmit 10 bits. Okay, but like of course, like this, all these modulation schemes work if the receiver is observing high SNR. Okay, if it is low SNR, then these modulation schemes don't work, and we'll see why. Okay, just to introduce this, why this like higher order modulation scheme work at higher SNR. Okay, we'll see that also. Now we are looking at this 5G, this QPSK modulation first, and this is the table. This is how it is specified in the standard. Okay, so what is happening here? Okay, so all these modulation schemes, they are complex. Okay, which essentially means what? There is like a real axis and there is an imaginary axis. Okay, and there's real axis and imaginary axis are typically represented in communication system as I and Q. I is basically called the in-phase component. Q is called the quadrature component. Okay, so what is this? What is this mapping? You take 2 bits. Okay, and then map it to one point on this complex plane. Okay, and what is this complex plane? This is the complex plane. Okay, right? And you look at this. So this is 0, 0. It is mapped to this point, 1 by root 2 and 1 by root 2. Okay, this is 0, 1. This is mapped to 1 by root 2. X is 1 and y axis is minus 1 by root 2. This is 1, 1 is minus 1 by root 2 and minus 1 by root 2. And this is minus 1 by root 2 and 1 by root 2. It's a very common QPSK mapping, okay, and because we are looking at it for the first time, giving it to you. Okay, this is called, this bit to symbol mapping, okay, is called gray mapping. Okay, if you have not heard it before, what is this gray mapping? Only one bit changes from here to here. You see this is 0, 0, this is 0, 1. Okay. From here to here again one bit is changing. Again from here to here one bit is changing. Okay. And the simple reason for doing this gray mapping is that if you make an error, if the symbol moves from here to here, okay, so what is happening? Only one bit goes into an error. Okay. If it is not, then if you don't do the gray mapping, 2 bits go into error. Then most of us understand, but I am formally introducing it. Okay. Right. And for all the modulation schemes, gray mapping is done just for this precise reason. Okay. Now, more crucially, from Scrambler point of view, okay, like what is, you look at these QPSK modulation, this is called a constellation plot, okay, and all the points in this constellation plot have equal energy. That is something we have to see, okay, all the constellation points have equal energy. Why? Okay, how do you calculate energy? Energy is basically the distance of a point from the origin, okay, right? And all these, what is, so this is, you look at this coordinate, what is this coordinate? Coordinate of this 1 by root 2 and 1 by root 2, okay, right. So what is the distance? Distance is I square plus q square. If this is I axis and this is q axis, right, okay. So the distance here is what? 1, right. Similarly, distance of this point is 1. Distance of this point is 1, distance of this point is 1, okay. So all the points are equidistant here for QPSK. Keep this in mind, okay, right. And that's crucial from a Scrambler perspective. So what happens here is that whatever may be the input bit, pair of input bit, okay, whether it's 0, 0 or 0, 1, what happens? You are going to transmit an equal energy constellation point, okay, because all of them have equal energy, right. Okay. Now, and that's, so what happens is, if all of them have equal energy, then standard, what it imposes a constraint, okay, it imposes a constraint that the average energy, average transmit energy should be unity, okay, right. And then how will you calculate the average energy of a bit sequence or this constellation, okay. What is this? We understand the notion of average energy, so you basically, how many constellation points are there? 4, right? So you take so E1, energy of 1 plus energy of 2 plus energy of 3 plus energy of 4. This is E average, right? Okay, so what is the average energy? 1 of this constellation, okay? And that's why the scaling is done. 1 by root 2, 1 by root 2, so that each of this point has a unit energy and average energy is 1. Okay, why is not 1, 1, right? Okay, so having told you about this QPSK average energy, okay, all the constellations which are defined in the standard have unit average energy, okay. It is not ensured that all the points will have the same energy when you move from QPSK to 16 QAM, I will show you that, okay, but the average energy of the complete constellation is going to be 1. Okay, we will see this, okay, right. So I hope this is visible. Can you see this, or should I zoom in into here? Is it visible to all of us? Okay, so you see this, okay. First thing, now what is happening here is, you look at each one of this, you are taking 4 bits and mapping again to one complex symbol, right, okay. So then what is happening? Each symbol is transmitting 4 bits. So each subcarrier is accordingly transmitting 4 bits, okay, right, that increases the bit rate, okay. Now, 2 things, okay, one is that now you look at the scaling is actually done by root 10, okay, right, and why root 10, why not any other number, okay, it comes from here, okay. So what is this? Now if you look at the coordinates, okay, what are the coordinates of this point? 1, 1, without scaling, okay. I am just for the time being I am not scaling it, I am just telling you how to calculate this number, okay. What is this? 3, 1, right, this is 3, 3. What is this? This is 1, 3. Similarly, you can calculate others, correct, okay. right? Now what is happening here? You look at this point, you can calculate its energy. Similarly, and what will be its energy? Okay, this is the distance square. Okay, so distance square is the energy. Okay, not the distance. I think in the last slide I told it is the distance square. Okay, so now what is, so you calculate the energy of this. Okay, right? So similarly, you calculate the energy of this. Okay, so this point will have a different energy than this because it is at a different distance when compared with this point. Correct? Okay, from the origin. Similarly, this will have a different energy than these two. Okay, and by the way, which of them will have the highest energy? This point, right? Okay. Now, if you calculate the energy of all these 16 points, you will see that it is of course not unity. But if you scale it, the energy will come out to be 10. Okay, and then you divide it by the square root of the energy, it scales to unity. Right. So what I am saying here is 1 by 16, if you calculate E1 plus E16, this is the E average, will come out to be 10. Okay. Then what are you doing? Okay. In order to basically normalize it to unity, you are scaling each one of this point by 1 by root 10. Okay. That is why this normalization comes. That most of us understand this, but for the students who do not understand, this is how it works. But the thing here is, from a scrambler perspective, is that all these constellation points do not have the same energy, unlike QPSK. Okay, and I just said that standard imposes this constraint wherein the overall average energy transmitted by the bit stream should be unity. Okay, correct? Now so this is how it is. Okay, 16 QAM constellation points do not have equal energy. Fine. Okay. Now what happens? As I said, let's go back to Scrambler. Okay. Do you have any control on what kind of bit sequence you will get here? You have absolutely no control. You are getting some message bits from here. Okay. Right? It is undergoing whole lot of processing. Correct? Okay. Fine. And that processing of course depends on the message bits, but at the end of this we don't know what sequence we have. Okay. We don't care what sequence we have here. Okay. But we care for the point that when you transmit at this, okay, the transmit symbol sequence should have a average unit energy of 1, right? Now what happens here if you get so that's where it is. So what happens here if you get let's say a long string of zeros at this point A, what will happen? If you go back, what happens here? If you get this long string of zeros, which constellation point are you going to transmit? You are only going to transmit this constellation point. Okay? You will not transmit any of the other constellation points. What is the average energy of this? Okay, much lesser than what you are allowed to transmit. What is the average energy of this? It is like 1 by 10 plus 1 by 10, right? X square plus y square. So that is, you have to calculate d square, that is equal to this energy. Okay, right? So this is 2 by 10. You are allowed to, your bit stream should, or the symbol sequence should have an average energy of 1, but you are transmitting at average energy of 0.2. Similarly, what about this point? If you, let's say if you get a bit sequence like this, 0 0 1 1 0 0 1 1 0 0 1 1, because you don't have control on the at this point A. Correct? So what happens here? You are transmitting, what is this? How much energy you are transmitting? 9 by 10 plus, okay. You are not allowed to transmit at this. You are violating the transmit power constraint imposed by statutory body. Okay, and you can be penalized for that. Okay, if I am allowed to transmit at, let's say 40 watts, I should only be transmitting at 40 watts. I cannot transmit at more than that, and that 40 watt is on an average, is the link. Okay, energy over let's say the bit stream. okay, right. So I am not allowed to transmit more than 40 watt, but what am I doing here? I am violating this constraint. Then you run into problem, okay. So what happens here? What is the scrambling doing it for you? It randomizes that bit sequence, okay. And once it randomizes, what happens? Okay, you will transmit on an average all these constellation points. And if you are transmitting all these constellation points, then the average energy reduces to unity. Fine? And that's the idea, that the scramble sequence is used to basically introduce randomness in the sequence, okay. And we see this, if it is QPSK, do you need the scrambler? Because all the points have unit energy, right? So you will never violate the transmit power constraints, okay, right? But there are other implementation constraints, okay. You should never transmit a constant sequence, okay, because it becomes like DC. And usually the transmit and receive chains have DC blockers, the capacitor put in the chain somewhere, okay. And then that sequence will get impaired, okay, it will get distorted, okay. That's more of an implementation constraint. Fine, okay. So scrambling enables use of inner and outer signal points in all these constellations, and then you are safe, okay. So that's precisely the reason behind using the scrambler. Fine, okay. So once we have understood this, we have basically understood the complete chain now, okay, because what did we just discuss? We discussed how scrambling is done, and before that we introduced the modulation also, okay. And modulation is coupled with scrambling in a subtle way, because if you don't introduce a scrambler, then you are going to, if it is an unequal energy constellation, you are going to violate the energy constraint imposed by the statutory body, okay. Fine. So that brings us to the end of this transmit chain, okay. But before we move into the receiver chain, I thought it will be a good idea to recapture this transmit chain from beginning till end and see how these different numbers pan out, okay. We will look at the transmit chain in parts in this class, and then half an hour in the next class, and then we will begin our receiver chain, okay, right. So this is what I am going to do, and then let us start that, okay. So I am not going to take any new example, okay. I am going to stick to the old example. So, and what is the example? Again, you should remember, right. So that we are looking at the MAC-phi interface, okay. Our understanding of this course is from phi's perspective, but phi has to interact with the MAC layer, okay. And then what does the MAC layer give? It gives a certain amount of data which is called a transport block, okay. And then this transport block is a function of data rate requirement of a user, okay. So in this case, it turns out that a user allocated 70 resource block over a symbol of 14 symbols. By the way, this decision is made by the scheduler, okay. We understood different kind of schedulers. Just to recapture, the most commonly used scheduler is basically the proportional fair, okay, which is neither greedy and nor it is inefficient, okay. The round robin scheduler is very inefficient because it does not use any channel state information. And then the max rate scheduler is greedy because it only schedules user with the best SNR condition, okay. Let us say there is a scheduler implemented in the MAC layer which has decided that this user should be assigned these many symbols and these many resource blocks, okay, over these many symbols. Then there is this MCS, it is assigned MCS 16, okay, which has a rate of this, okay, right. We are only recapturing whatever we have done, okay. So depending on this assignment, right, MAC will send a transport block of size these many bits. This transport block size needs to be calculated, okay, and MAC layer does that. Where does the intelligence sit? In the MAC layer, okay. And then that formula to calculate this is exactly defined in the standard, so MAC layer should know, okay, right. Now once this is done, physical layer doesn't decide on anything. Okay, it is because the decision has already been made by the MAC layer that this has to be transmitted. Physical layer is dumb. It does brute force processing, and we have seen that. We are going to again see it. Okay, so what happens first? You have a transfer block. Immediately after that, transfer block CRC is appended. Okay, then it is segmented. Okay, why is segmented? Because 5G LDPC encoder can process only 8448 bit for first base graph, and for second base graph it can encode 3840 bits. This is denoted as KCB. Okay, now most of us should remember these alphabets. Okay, they should come in your dreams if you are actually like working day in and day out on standardization. Okay, and then this transfer block should be segmented if transfer block length plus 24 bit CRC, okay, is greater than KCB. This number is denoted as B. Okay, the whole of this length is denoted as B. Fine. Okay, so but this segmentation, we understood it is closely coupled with LDPC encoder design. Okay, because LDPC encoder cannot encode any arbitrary segmented code block, size code block. Okay, so what did we learn? We learned was like this total number of segmented code block. How do you determine it? If this B is greater than KCB, okay, L is basically code block CRC. Then how many code blocks? This is the total size B divided by KCB, that's the maximum length 8448. I have minus of L because you are leaving place for the code block CRC, right? Okay, and then what is the actual payload? Payload is B dash, it is different from B. Why B dash is different from B? Because you are appending C extra code block CRCs, each of length L, right? Okay, so that's the payload you need to transmit now. So if B is less than KCB, then there is no code block CRC. Segmentation module implements that, we have seen it, right? Okay, then the code block is 1 and B dash is equal to B because L is 0, right? Okay, so that's typically how it should be segmented. Okay, there is an extra notion of filler bits. Okay, so in our example, what is this? This was B. So if you substitute these numbers here, B is this 28192, then KCB is maximum 8448 minus 24, you get 4. Okay, right? And then B dash, if you substitute these numbers, B plus C into L, you get 28288. That's the actual payload you need to transmit, right? The subsequent blocks need to take care of this because this should be modulated and transmitted on air, right? Okay, so each code block size is K dash, this is B dash by C and 7072, okay, right? But it is not done like this, okay? And why it is not done like this? Because as I said that LDPC encoder cannot encode any arbitrary size like this, okay? So we'll start from here in the next class, we'll take a break, okay, and then we'll come back to the next class. Thank you.